Hello, everyone. Welcome to the third session of parton densities and structure, proton structure. Today, we will begin our first session with talks continuing about PDFs with some contribution from the lattice perspective in the latter half of this session. And we'll go ahead and get started to make sure we have enough time. For the speakers, I will keep track of the time and let you know when there are 5 minutes left, and then when you need to wrap up. And then we'll have 15 minutes and then time for 3 minutes of questions. So without further ado, let's get started. Pitt, are you able to share your slides?
Yes, give me a second. Okay, I hope you can see it now.
Again, we can hear you well. Please go ahead.
Okay, then thanks for being here, everyone. Thanks for listening to the talk. And my talk will be about the impact of inclusive hadron production data on the nuclear gluon PDFs. And yeah, before we go into the fits themselves, let's go to a quick introduction of why we want this data, what's the theory, and how to do predictions for this data. So at the very beginning, let's start with the current status of NCTEC. The PDFs shown here are the LED PDFs of NCTEC 15, which is our latest main release. And the labels are a bit small, but I hope you can see the valence quark uncertainties are already rather small. But if you look at the uncertainties of the C quarks and especially the gluon, which of course via declap evolution contributes to the C quarks, they have rather large uncertainties, and we'd like to get these uncertainties down as much as possible to allow for precise predictions for any future experiments involving hadrons in the initial state. So yeah, this is basically the latest main release, and we're of course working on many different angles to improve. For example, yesterday already you may have heard the talk by Falk about including the neutrinos in the fits, and also about NCTEC 15 WZ, which we've recently published and which is also quite important for this talk, as you'll see later. And right after this talk, you'll hear a talk by Efrain about NCTEC 15 high X with improvements at the high X region. So yeah, let's get a quick reminder how the PDF fitting in our framework works. We take this as an ansatz for each PDF flavor that we include in the fit. So for example, up quark, down quark, gluon, or the difference between up and down C, where we have a total of 6 parameters, and at some initial scale Q0, from which we then go to higher scales via declap evolution. And each of these 6 parameters gets a nuclear correction by this parameter A, which depends on the nuclear mass A via this parameter B. And the P parameters are fixed from some proton PDF fit, namely the CTEC 6M. So then the total nucleus is just the sum weighted by the nuclear charge of the proton, these effective bound protons, and these effective bound neutrons, which are just calculated via isospin symmetry. And then the open parameters, we have a total of 19, which is 3 parameters more than NCTEC 15 used, which are these strange parameters. So NCTEC 15 basically just had a fixed strange that is just determined by a ratio of the U bar plus D bar, but now we actually fit strange as an individual flavor, we include these parameters because they were also included in NCTEC 15WZ, which was include the first datasets that actually put reasonable constraints on these strange PDFs. And since we want to compare with NCTEC 15WZ, we also include these parameters in this fit. So why are we even interested in single inclusive hadron production? There are two reasons. The first is that this process, contrary to DIS and Rayyan, is sensitive to the gluon PDF already at leading order and not just via deglab evolution. And in the recent years, we got some precise new data from Alice. So of course, we want to make use of this data. And to show you how sensitive this process is to the gluon PDF, I have these two plots, one at RIC energy and one at Alice energies. And each color represents the fraction that is contributed in a proton-lead collision producing a pion by each of these PDF flavors. So at low energies and low PTs, the gluon dominates, and then slowly, when going to higher PT, the up quark becomes more dominant. But at the Alice energies, the gluon, even at very large PT, is still completely the dominant factor. So including this data should help us constrain the gluon and bring down the uncertainties, hopefully. But there are two problems actually with including these data sets. First is the very precise data is in the low PT region. And when we go to too low PT values, we can no longer guarantee perturbativity, which of course means that the data cannot be used in the fit. Otherwise, we'd just be fitting theory errors into our PDFs. And the second problem is that single inclusive hadron production is dependent on the fragmentation functions, which means that, which are also non-perturbative objects, just like our PDFs that we want to fit. So we have to somehow take care of the uncertainty that comes from including these fragmentation functions in our theory. So as a first step, we take a look at different fragmentation functions that are available. This is not an exhaustive list, and this is just for fragmentations into neutral pions. And we compare with data once from Alice for proton-proton to pi0 plus something, and for Phoenix data. And we see that above PT equals 3, all the PDFs can describe the data in a reasonable manner, but there's always some normalization factor that doesn't match up. But this is not a problem for us because we are going to fit nuclear ratios. So the ratio of cross-section in PP, or the ratio of some nuclear cross-section over the ratio of PP. So any normalization just cancels out anyway. So this is not a problem for us. The only fragmentation function that somehow doesn't quite fit into in with the others is jam20, which drops off a bit, below around PT equals 5. So as we'll see later, this is slightly problematic for this particular fragmentation function. And then here I have charted the data that is now available. These first two sets were actually already included in NCTEC 15 and also EPPS 16, which is neutral pion production at RIC. And now we include Alice data sets, one's at 5 TeV and one's at 8 TeV. For neutral pions, charged kaons, and eta mesons. So as you see, some of the data sets have a large range in PT, but many of them also go quite low in PT, which means they're going to have to be cut due to our perturbativity concerns. So if we just look at the data directly and compare fragmentation functions for all the available data sets, first just using the NCTEC 15 WZ PDFs, we can already see that most of the data is quite well described, even without including them directly in the fit. And we also see that the fragmentation functions of DSS, BKK, and KKP match up almost exactly, while NNFF and JAM20 are mostly very close to them, but in the high PT region for neutral pion production, they are slightly outside of the uncertainty bands that are calculated from the DSS eigenvector sets. So yeah, here's basically showing the same for charged kaons and the eta mesons. For the eta mesons, there's only one fragmentation function available, which is AESSS. And this fragmentation function also doesn't allow calculation of uncertainties, which is unfortunate because so we can't estimate how accurate our predictions for these eta mesons are.
You have 5 minutes left.
Oh, okay. Yeah, then let's go to the fits. We include all the same data as in NCTEC 15 and NCTEC 15 WZ. We repeat each fit twice. And we remove the eta meson production data for the reason I just mentioned. We cut the data below PT smaller than 3 GeV. As mentioned in the proton-proton, we can't describe the proton-proton case, so we aren't sure that we can describe the ratios. Then other settings are basically the same as NCTEC 15 WZ. We open up the normalization parameters for all the sets because they have large uncertainties. And we use DSS fragmentation, which is the one I was showing with uncertainties before. And we add these uncertainties onto the data systematic uncertainties to compensate for our fragmentation function choice. And this is the resulting fit based on NCTEC 15. So without WZ for now, we see quite an enhancement in the low X gluon, but the uncertainties actually don't really shrink. But we even see larger uncertainties in all quarks, but this is mainly due to the opening up of the strange parameters. This was also seen in the NCTEC 15 WZ fit, so this isn't surprising. And if we use NCTEC 15 WZ as a basis, we see basically no changes in the up and down flavors. We see the gluon change shape quite by a bit. This bump right here vanishes mostly, and the uncertainties in the medium X region shrink. Or I should mention what the red and green are. Red is the fit without the DSS uncertainties included in the data, and green is with these uncertainties included in the data. So of course the red band will always be a bit smaller, but it actually doesn't make that much of a difference. And something we see right here is the strange gets enhanced quite a bit, even though if you remember back in slide 3, the single inclusive hadrons are actually not sensitive at all to strange. So this is actually the impact of the WZ data, given the changed gluon shape from the single inclusive hadron data. And if we just look at the chi-square values, we see that NCTEC 15, this already looks reasonable at first, but if we look at how much better it can get, this no longer looks reasonable. So yeah, if we include the data, we can get very low chi-square, and including single inclusive hadrons improves WZ, and the reverse is also true. And including both gives us, of course, the best chi-square value, and it looks compatible with all the other data. If we compare different fragmentation functions for our final fit, they all deliver quite good chi-square values, all smaller than DSS if we don't add up the DSS uncertainties to our data, except for JAM20, which I mentioned already earlier, which fails to describe the proton-proton baseline down to 3 GeV. So this explains that. And yeah, here are just some comparisons to the data after the fits. there's not really large qualitative changes, but yeah, especially compared with the bare NCTEC 15, we see quite some improvements in the lower PT region. Yeah, also the same for the other data sets. And then
one
there's
1 minute left.
Yeah, one more fit with the ITA data included, just as a check. We see in the NCTEC 15 case, this just makes it minor, even further improvement, change in the gluon, while in the NCTEC 15 WZ, the impact of the ITA data is completely negligible. So it's not too bad to exclude it because we also don't know how much uncertainty we should add. And concluding, we can account for the fragmentation function uncertainty by adding this uncertainty on top of the data. Sadly, we have to cut all the data below PT equals 3 GV to ensure validity of our theory, but this still helps us constrain the gluon, especially in the medium to low X region. And that's it. Thank you all for listening to my talk.
Great. Thanks so much for being exactly on time. So that was very good. Now we have time for some questions. I see there's, first Tanu. Please go ahead.
Yeah, so I heard that, if I heard correctly, that you still use as a baseline PDF, proton baseline, a CTEC 6M. Was this correct?
Yes, this is the same as
So,
was used in NCTEC 15.
So the question is, why do you use such an old baseline? I mean, it's like 15 years old. So also part of the difficulties you guys find with the neutrinos, I mean, could be due to the baseline PDF. So what's the reason for using it?
I don't know how much it would help in the neutrino case, but for all the other data sets, it seems sufficient for now. I guess this is certainly something that should be updated at some point, but for now it has worked for us, so we haven't changed this part.
All right.
Maybe now a quick question from Pia.
My question is very, very simple. You have a 3 GB cut in the PT for your data now. Yes. However, the DSS latest analysis from 2014 for the Pions have a 5 GB cut for the Alice data because they cannot fit together Rick and Alice. How do you have any insight of how would your results change if you added that higher cut?
Yes, of course, if we cut even higher, then the impact of the total data set gets lowered, especially in the very low X region, because the higher one goes in PT, the higher the X is affected.
And then I have a really good question. Why would you lower your cut to 3 when you know your baseline fragmentation functions are not supposed to work at 3?
Well, as shown in this plot, we can describe the proton-proton baseline up to 3 GeV, so I don't see an issue there.
Well, they claim in the paper they did the analysis. I guess they know better, but whatever. Thank you.
I think the difference is they used different scales for the fragmentation and renormalization. And if we look at different scales, it actually doesn't work down to 3 GeV. So that might be a reason why it didn't work for them.
Okay. Yeah, unfortunately, I have to move on. I see there's a hand. Maybe we can follow up in the chat with additional questions and discussion. So thanks again, Pit. And now we'll move to Efrain.
Okay, thank you very much. Let me just share my screen, hide these meeting controls. I'm just going to just say hello on video and then turn off my video so my internet runs smoothly. So thank you very much for the opportunity to speak today. I'm going to be talking about NCTEC 15 high X, in particular nuclear PDFs in the valence region. And this is work in collaboration with a lot of people, some of whom are here today. And if you want the full story, I'd say please check out the archive, which is currently under review. So thanks to Pitt, I don't have to go into a lot of detail about the NC-TEC 15 framework. And this is an extension to that framework, the HiX, as he mentioned. And the bottom line that I want to present and work up to today is essentially our new analysis of pushing into the valence region and extracting nuclear PDFs with a particular interest on the U valence and D valence, or U and D PDFs. So what I'm showing here, and what I'll explain as I go through the talk, is how we extract the NC-TEC 15 HiX, which are the PDFs in the gold bands relative to NC-TEC 15. And what we see is a markedly different behavior, especially at HiX, where we have an increasing strength of the U and D PDFs as a result of new data and as we push into this valence region. So not only are these nuclear PDFs in the valence region useful for any analysis that is sensitive to very, very high X, but in particular, a lot of the theoretical ingredients that we've built into this framework are, I would say, pretty important as we think about a future EIC and moving forward in future analyses. So just as an outline today, what I'm going to be talking about briefly are the challenges that are associated with moving into the valence region, and then also just basically presenting the resulting PDFs, which we call NC-TEC 15 HiX. And again, if you want the full story, please check out this archive link, which is currently under peer review. So what I'm showing here is just a landscape of data that's used for nuclear PDF fitting by the NC-TEC collaboration. On the X is X, on the Y-axis is Q squared. And in the original NC-TEC 15 paper, what was used is a kinematic cuts that required pretty clean DIS events, Q squared greater than 2, W greater than 3.5. So that's this entire black shaded region here. What we wanted to motivate is, you know, a lot of the data start to run out of steam around X of about 0.5 or 0.6, where you have very few data points available to help constrain your PDF at high X. And in particular, these data sets, especially at high X, suffer from having pretty large uncertainties at high X. What was noted is that there's actually a large data set at pretty low Q and low W, but at high X, from Jefferson Lab during the 6 GeV electron beam era. A lot of these data sets are nuclear DIS data that span a wide range of nuclear targets. And what's of extreme importance is that all of this data actually has pretty high precision. And so if we can lower our kinematic constraints and start to look at this data, include this into our analysis, this will provide a pretty important benchmark at high X to constrain the PDFs. And so NC-TEC 15, what we've done is lowered our kinematic requirements to Q greater than 1.3, W greater than 1.7. So as we're including a lot more low X data too, we start to scrape the top of this really high precision nuclear DIS data that's available. And so that's what we're going to be doing as we move forward. So some of the challenges that are associated with going into that valence regime is that you really start to test the flexibility of your parameterization. So as you start to get high precision data in the EMC and Fermi smearing region at high X, you're going to be testing that X parameterization, how flexible that is, as well as you're going to be testing the A parameterization. And I'll show a slide in a little bit more detail about that. Not only are you going to be testing your parameterization, but you're also going to be now sensitive to the deuterium calculation that you do in theory as you compare it to data that's traditionally reported as cross-section ratios relative to deuterium. And so how exactly we calculate deuterium for the denominator becomes pretty important. And again, I'll show a slide in a moment on that. And lastly, what becomes important also are target mass and higher twist effects. As we go into lower Q, these become more and more important. So just to the first point about the parameterization and making sure we have the flexibility to describe this data, what I'm showing here is just cross-section ratio of carbon relative to deuterium as a function of S. So this is just some DIS data that I'm showing. In black are all of the data points that were previously included from using the NC-TEC 15 kinematic cuts. So this is, again, the pretty high Q and W cuts. So like I noted, a lot of the high X data has pretty high uncertainty. As we lower those kinematic cuts, we're more sensitive to the points now in red. So the open squares are all of the JLab 6GeV nuclear DIS data. And so this is what I mentioned, that all of these data have very high precision that we can use to constrain nuclear PDFs all the way out to high X. What's currently excluded is a lot of the data that extends to very, very high X and starting to get into the Fermi smearing region. But these would be included if you further lower those kinematic requirements. But not only are you trying to describe this, how the PDFs look like as a function of X, and you want to get the shadowing, anti-shadowing EMC region and start to get into the Fermi region, all of the JLab data are very precise over a wide range of A also. And so this spans from helium all the way up to gold. This will really test the flexible parameterization that we have in A, and we can really understand if we have a problem with our A dependence or our X dependence, et cetera. As I mentioned, also deuterium becomes pretty important. So the data are traditionally reported, or at least the DIS data are traditionally reported as cross-section F2A relative to F2D. However, in NCTEC 15, what was actually calculated was F2A, but the denominator was P plus N and not F2D. And so essentially this is wrong to the level of how different D is from P plus N. So what I'm showing here is exactly that ratio as a function of X for 2 fixed Q squareds for the different colored lines. And so while in NCTEC 15, you had these kinematic cuts that essentially restricted the data to about X of 0.6 or 0.5. And so this, this error is really only the percent to maybe 2% level. However, as we extend into that high X region, we're going to be now pretty dependent on the exact nature of how wrong D is from P plus N. So the approach that we've used in NCTEC 15 high X is essentially we again calculate F2A, but now we have a fixed F2P, and we essentially evolve the data from F2A, instead of being reported as a ratio to F2D, we essentially multiply by parameterizations of F2D over F2P. So essentially what we're doing is we're now comparing apples to apples, but we're using a parameterization for the data to go away from D and to P so we can calculate the same thing. And that's just showing, what I'm just showing here is the ratio of F2D over F2P as a function of X. So this is that evolution factor that we have to apply to the data to then compare it to our calculation. Lastly, what's also important, as I mentioned, are just low Q squared effects. So we're sensitive now to target mass effects. These are subleading, essentially M over Q corrections to the leading twist structure function, which are theoretically well understood. And what's also becomes important are potentially higher twist effects. So what I like to think of when someone says higher twist are these non-perturbative multi-quark interactions, or essentially the dynamics that allow for one quark to carry all the momentum as we approach X of 1. Because they're, non-perturbative, they're very complicated, they're not theoretically well understood. And often what's done is just, these corrections are parameterized as a 1 over Q squared like dependence, and you essentially fit some functional form to extract these higher twist effects. So what we did in NCTEC 15 is we just used actually the CJ higher twist effects and put that into our framework. So the approach to NCTEC 15 high X was the following. We included all of the JLab 6GeV DIS data that's within reach with our kinematic cuts, with these lower kinematic cuts. We actually removed all of the isoscalar corrections from the NCTEC 15 database. And then we lower those kinematic cuts down from NCTEC 15 to this high X region where we're going to Q greater than 1.3, W greater than 1.7. And effectively, that more than doubled the amount of data that we consider in our PDF extraction. So one thing that you can just look at is see how NCTEC 15 works out of the box. Again, this won't be too great because one, we remove all of the isoscalar corrections. So this is not the exact data that was fitted originally to NCTEC 15, but also we have lower cuts and new data. We then do a simple refit of NCTEC 15. And then we start including all of these corrections to get to NCTEC 15 high X. So this includes the target mass and higher twist. This includes just the deuterium to proton evolution, and then this includes both of the effects in NCTEC 15 high X. So what I'm going to show you is a chi-squared, essentially landscape, where each row is going to be each of these individual trials, essentially. So what I'm showing here on the top is this NCTEC 15 out of the box. This is chi-squared per degree of freedom as a function of experimental ID, which isn't too relevant, but I just want to highlight that in blue are the previously used DIS data sets in NCTEC 15 with these lower cuts. In green is the Drell-Yan, and in orange are these new JLab data that we're sensitive to with our lower kinematic cuts. And so out of the box, NCTEC 15 actually does a pretty bad job, I would say, especially at describing all of the new data set. If you do a simple refit of all of that data, you actually achieve a pretty reasonable description overall of all the data sets. And now as we add higher twist and target mass, that has a pretty negligible contribution, but a small improvement. And the biggest actually comes from essentially treating deuterium correctly. So again, this is instead of calculating P plus N and comparing it to deuterium, we fix the proton and we compare the data to relative to the proton. And so this actually has a pretty big impact, especially at all of the JLab data, which has high precision at high X. And lastly, if you include again the higher twist, you get a small improvement of the overall chi-squared. So NCTEC 15, I would say, does a pretty good job at describing the data well, all of this high precision data. So what I'm just showing here are these EMC data sets that have been evolved relative to the proton now for a wide range of A, from helium all the way up to lead as a function, or gold as a function of X. I'm highlighting all of the JLab data by essentially looking at a linear scale in X, and we do a pretty good job at describing the data within their uncertainties. What I'll say is important is that, and what we expect is that this JLab data has added tighter constraints on the U valence and D valence in particular. So what I'm showing here is just a chi-squared landscape for one of the parameters that control the U valence PDF. And what we see is that in blue is the chi-squared contribution to NCTEC 15, the original data sets with the lower kinematic requirements. And in red is the added JLab data, which has high precision at high X. And of course, what you see is in red, you're adding a tighter constraint on this parameter, slightly shifting the minima. So overall, you have a better idea of where this parameter lives, or the uncertainty is smaller, and you have a slightly new minimum with respect to the NCTEC 15 minima. And so overall, what we see is that these resulting nuclear PDFs actually have a pretty new behavior, especially at high X. So again, what I'm showing I'd like to highlight is gold, which is the NCTEC 15 high X PDFs. These are the bands also include the uncertainties. And this is relative to NCTEC 15 baseline. And so at comparing gold to blue, what we see is we have a reduced uncertainty at high X, which is what we expect, particularly in the U and D, which are essentially all of the parameters that we're opening up are related to the U and D. And we also have a shifting of strength from low X to high X to help describe the EMC data at high X. And I'll just note that this is on a log linear scale if you're staring a little bit at this plot.
Sorry for not giving you an earlier warning, but you have about a minute left.
Okay, great, thank you. So I'll just want to end actually with a warning that we actually, with these lower kinematic cuts, we actually don't use too much data above X of about 0.7. And this is essentially we're not constraining the region that starts to get into the Fermi smearing region. But this is an ongoing project, I'd say a work for the future, and I'd just say stay tuned for that as we move forward. I'd just like to again highlight and say check out our work. It's currently on the archive under peer review. This is a comparison of all of the PDFs now relative to different groups out there. These can all be updated based on all of the work that we've seen at this conference so far. But I'd just like to say thank you. If there are any questions or comments, I'd be happy to take those.
Fantastic. Thank you so much, Efrain, for sticking to time. That was very interesting. Then now I have time for some questions. Maybe I can ask just a quick one. On I think it was page 15. It seemed like the very highest X points in all the different data sets were a little bit off. I know that their errors are big, but can you maybe just comment on that briefly?
Yeah, so that essentially gets into our future work of trying to describe. Let me actually go to this slide here. Sorry. So essentially what we noticed when trying to describe even lower kinematic data, so going to very, very low W and trying to get into the Fermi smearing region. So what I'm showing here, I'll just focus on this panel here, or actually iron works fine. So these gray points have not been included in the fit. What we notice is that as you start to turn over in this Fermi smearing, which are those last points that you were seeing in that previous plot, we start to have a little bit trouble in capturing exact location of the dip and how steeply it needs to turn around to reach the Fermi smearing region. So that's not well described currently, and that's if you lower the kinematic cuts even more, that becomes more and more apparent that we just can't exactly capture this turnover. But that's, I'd say, a work in progress, and stay tuned. But that's exactly what you're seeing in this plot here.
I see, great, thanks. I see a hand up from Hannah, maybe just a quick question.
Yeah, so you mentioned that you include now some extra higher twist contributions as well. So what is their role, or have you checked out how would your fit change, or would the quality change if you would not include such a terms? And
yeah,
you find
so
some evidence for the A dependence of those higher twist terms.
Yeah, that's a great question. So we included higher twists and target mass corrections within the fit. I'd say it has a pretty, so what we did is essentially we took it as a fixed correction using just CJ input for the higher twist. They didn't have a large effect, just higher twists. It had a pretty small effect, but we didn't explicitly look for opening up parameters that describe higher twists and trying to do that. Certainly that could be an avenue for the future, trying to explore that, but we didn't do that in this work.
Right. All right, thanks, Efrain. I think we have to move on. So now let's go to Wayne.
Hi, yeah.
Okay, we can hear you.
Hang on. Need to find the slides. Okay. All right, can everyone see that?
Yep, we see it. Please go ahead.
Okay, cool. So I'd like to start by thanking you for the introduction, and I'd like to thank the organizers for this conference for making this all possible. I was going to turn my video off. Oh, here it is. Okay. To make sure it doesn't, for connectivity. Okay, so I'm going to talk about gluon pseudo-distributions at short distances in the forward case. This is some work I did with Ian Blutsky and Anatoly Radushkin as part of the hadron collaboration. So the motivation here is that lattice calculations of PDFs are a subject of considerable interest and efforts, though they run into some issues that they can't be directly calculable given the issues pertaining to Euclidean space, going into Euclidean space for the lattice. Yes, the one solution that was proposed in 2013 by G was this groundbreaking proposal to consider equal time versions of non-local operators, or quasi-PDFs, which from which you can obtain your light cone PDFs in the limit of large momentum. So the idea was to take these space-like separations, which avoids the issues of Minkowski to Euclidean space. Then from there, Anatoly Radushkin in 2017 proposed these pseudo PDFs, which also use this space-like spatial separation. But in this case, we stay in the coordinate space and we obtain our light cone PDF in the limit z squared goes to 0. So if we take this this space-like separation, well, we have the PDF, the pseudo PDF can be represented as this integral over the alpha time, where the alpha time nu in our case is P3 times Z3. And if we take just now the Z3 to 0 limit, we should get the pseudo PDFs. So a feature of the pseudo PDFs at this small Z3, the inverse of Z3 is analogous to the renormalization parameter mu of the scale dependent PDFs from the standard OPE approach. The only issue arising from the fact that the C3 squared dependence comes from both evolution logarithms and ultraviolet logarithms. So we need to first remove that in order to just have keep the Z3 dependence coming from the evolution terms. Now, since the UV terms turn out to not be dependent on the alpha time, we can take this reduced alpha time distribution which is this ratio here, I should say reduced alpha time pseudo distribution in this case, where we take the alpha time distribution divided by the same quantity at 0 alpha time. And because, well, if you make sure that your quantities are multiplicatively renormalizable, the ultraviolet terms drop out. So from here, we can get this evolution equation where, again, we have this Z3 squared playing the role that the parameter mu would have played. The last thing here is that when you take this Z3 to 0 limit, you end up with these singularities, and so you need to find matching conditions in order to get the PDFs from the lattice data. So to start, I'm going to talk about the method of calculation. For Gluon calculations, they're, as y'all probably know, are very complicated, partially due to the gauge invariance. And so an effective way of approaching this was to use the external field method along with this Schwinger representation for the propagator, which is outlined in a paper from Belitsky and Brown from 1988. The external field method involves separating your fields, your gauge and your Fermat field, into a quantum field that has some virtualities between, say, mu2 squared and mu1 squared, and this slowly varying, in quotations, classical field that have virtualities below this mu1 squared. And so if I rewrite my Lagrangian, absorbing the coupling constant into A, the gauge field, you get the Lagrangian like this, where you have this classical, this filtering tensor written in terms of just the classical gauge fields, and then these extra terms written in terms of the quantum fields. Similar deal for the fermions. And then of course you have your gauge fixing and your Gaussian terms. And one other thing is this covariant derivative is just written. This is not the regular covariant derivative. It's the covariant derivative with just the classical field here. So from there, you have two different gauges we use for the two different types of fields we're looking at. For the quantum fields, we use this background field gauge, which at this order in the calculation coincides with the Feynman gauge, and then the Fox-Schwinger gauge for the classical fields, which is this Z contracted with the classical A 0. So this gauge leads to a really nice relation between the gauge field and the field strength tensor. So you can write the gauge field in terms of this integral over the field strength tensor. And then also we have this Schwinger representation for the propagator, where we write the propagator as this integral over this parameter S. And of course, having this regulating term. So the first thing you do is you write your Gluon propagator out. And in terms of the Schwinger representation, from here I've omitted the epsilon term just for convenience. Then you expand over this parameter S, then integrate back over it and also over the momentum. This is an okay thing to do because higher orders in S also come with higher orders in Z squared. And because this is a small distance expansion, a small Z expansion, it's well behaved. So one other thing to mention about this external field method is that diagrammatically, you get, I guess you could call it a simplification, just in terms of like having less diagrams to have to think about. Basically, in the way you would think to do it, usually, instead of writing out your Feynman rules, you'd have this vertex graph and this graph here with the insertion from the gauge link into the vertex. But these are both represented by this single graph that we just called the vertex graph in our case. The major reason why I bring this up is because each of these graphs independently carry a linear divergence that just implicitly cancels in our case. And you can see the remnants of that with these 1 over d minus 3 terms down here. And this here is the vertex, our vertex result, just with 4 open indices. Those 4 open indices being 2 from each field strength tensor. So the object we're calculating is this spin average matrix element, the forward case. And we calculate this with all the indices open, taking no projection. One of the highlights of that method is that we can do some manipulations of this to get things like the helicity distribution just by throwing in a Levi-Civita tensor. It's fairly straightforward once you have that general result. Of course, we have we use the straight line gauge length with the adjoint representation. And then we have this Lorentz decomposition of this matrix element. Now, if I take the light cone projection, the only surviving term is this MPP term. And so that is what we want to look for, because this is the Yaffe distribution that gives us our Gluon PDF. So the idea is to isolate the MPP term in our calculation. So now, in our case, we're going to take some other projections. There were 3 projections that were found to be multiplicatively renormalizable by Xiang et al. In 2018. These quantities were this 3i I3, 0i I0, and 0i I3 plus 3i I0. So we ended up going with the 0i I0 term because it has the least extra terms from higher twist contributions. And what we also found was that if I take this MJIIJ projection, I'd get this minus 2mg, which exactly cancels with this 2mg from the 0i I0. And conveniently, that term shares the same anomalous dimension with the 0i I0 term. So that's the quantity we want to look at, because it just gives us this MPP term, which is what we're looking for.
Hey, when you have 5 minutes left, just let you know.
Oh, all right, thanks. So the leading twist gluon calculation result is given here with the usual evolution kernel from the coordinate space calculation. We have this constant part, and then we have this UV part, which again will cancel when we take this ratio here that I mentioned earlier in the talk. And so with our so this is our reduced Yaffe time pseudo distribution. The next thing to talk about is the gluon quark mixing. This is the result you get, where this operator is a singlet combination of quark fields, and where F is, of course, the sum over those with evolution kernel. Again, what you'd usually get from the coordinate space calculation. This needs to be manipulated a bit to get into the form we want, especially to deal with this 1 over Z3 term. Well, again, it's fine because this goes to 0 as Z3 just goes to 0, so it doesn't. There's no issues there. That's not like a singularity or anything. So we relate it to the Yaffe time distribution through the following relationship. It can be shown that you can do this by taking the parameterization of the matrix element and taking advantage of the oddness in Z3. And so we get this new kernel, which is an integral over the old kernel, and it's right here. So finally, we can write our matching relation. Again, we have our evolution type term from the gluon and from the gluon quark, and then we have this log part and constant part that we need to deal with. So these i's being our light cone Java time distributions, which can be related to the PDFs in the usual way. And we also have this F distribution n equals 0, which turns out to just be this first moment here of the gluon PDF. And so using these relationships, we can put this matching relation into a new form in terms of the light cone PDFs, where we have these new R kernels, these moments X, and this reduced Java time distribution, and our gluon and quark, singlet quark functions. And so the next step would be to independently calculate your moment and use some estimate for the singlet quark function, and then you can fit for the gluon distribution. The R kernels are basically just a cosine transformation of the old kernels. For the gluon kernel, we have this term, where this is from our first term in the matching. Then we have our evolution type term, log term, and constant term. And then we have, again, the same process for the mixing kernel right here. You can integrate these. It's pretty straightforward. The RL gives this hypergeometric function. The other terms that give just some combination of sine integrals, cosine integrals, sines, cosines, and inverse powers of y. The key point, though, is that those R kernels are they're given by explicit perturbably calculable expressions. And so we can directly relate the lattice data to these light cone PDFs. So what we have to do is take some parameterization of the gluon and the singlet distributions, and we can fit those parameterizations and our coupling from the lattice data. This is analogous to the good lattice cross sections approach given by Ma and Chu in 2018. And then finally, just some ongoing work we're doing is we have a paper on the gluon helicity pseudo-distribution on the way. Currently in the middle of working on the transversity quark pseudo-distributions, and also working on a gluon condensate calculation. And lastly, I'd just like to say thanks, and to shout out to the Hadstrut collaboration, so everyone involved in that. And yeah, thank you.
All right, great. Thanks, Wayne. Now we have time for some questions. I have just a really naive question on page 4.
Okay.
Yeah, just sort of basic. So why does the covariant derivative use the classical vector field?
Oh, okay. So that's really just when you write it out and you reorganize the terms into some way, that's really just how it turned out. The idea being is that we want to use that definition for the covariant derivative and in our definition of the gauge, the background field gauge here.
I see. Thank you.
Yeah. Okay.
I don't see any other questions. So thanks again, Wayne, for this interesting talk, and also for keeping to time.
Yeah. Thank you.
And now we will switch. We'll now go to the next talk, and I'll also hand over the chairing of the session to Pia.
Right. So our next speaker is Xiang Gao. So we will continue with Lattice perspective of PDFs. Xiang, if you can show your slides, please.
Yeah, sure.
So I will let you know when you're You have 2 minutes left.
Okay.
So
okay,
please go ahead.
Okay, thank you. So today I'm going to talk about the Pion structure and form factors from lattice calculations at physical point. So as we know, Pion are generated by the called snowballs generated by the characteristic simultaneous breaking of QCD, so that it's play an important role in the study of strong interactions. Meanwhile, in the Carroll limit with massless quark, the Pion mass is also approaching zero. Therefore, it's very puzzling how quarks and gluon move and interact inside the Pion. However, as we know, Pion decay force, it's hard to have the fixed Pion target, so that the Pion structure is less constrained compared with the proton. So there are still some puzzles. For example, one of the issue could be the approach one asymptotic behavior of the Pion valence quark PDF. As you can see from this figure, the result from the global analysis of GM, ESV, and the calculation using Dyson-Schwinger equation produce an inconsistent result, which are beta around 1 or beta around 2. Now we are trying to use the Lattice QCD technique to investigate the Pion valence structure. However, as we know, PDFs are electron quantities, therefore cannot which are unequal time, therefore cannot be directly calculated from Euclidean Lattice QCD. It was proposed by G that instead we can compute the matrix element of the equal time operator. For example, you have a have operator using psi bar separate along with spatial direction but equal time. And you have a hadron with large momentum PZ. Then you can define the quasi-PDF by the Fourier transform and match it to the PDFs. Or we can also perform the factorization as what we do in this talk. Factorization in the coordinate space. In this way, the matrix element of the equal time operator can be related to the moments of the PDF by the Wilson coefficients, which can be computed from the perturbative theory. And of course, we have the power corrections proportion to this squared. Therefore, we are limited to short distance. And since the moments are surprised by the factorial of n, we need a large ZPZ to get access to the higher moments of the PDF. Therefore, large PZ is essential for this methodology. Of course, from lattice, what we compute is the Bayer matrix element, and which need to be renormalized. We know that the operator can be multiplicatively renormalized and is independent of the hadron state. Therefore, we can construct the proper ratio to cancel the renormalization factor. For example, we take the hadron state with different momentum. Then we can plug in the formula above into the into this ratio and fit our lattice data to extract the moment of the PDFs. So firstly, we have a calculation with empirical Pion mass with two very fine lattice spacings. The largest momentum we have is around 2.5 GeV. In these calculations, we are able to extract a reasonable signal of stagnant force moment of the Pion valence PDF. And our continuum estimate have a good agreement with X feeder and GM18 result. And then, of course, we can take a proper model inside, put it inside the formula in last page and fit our lattice data, then reconstruct X-dependent PDF, which is showing as the blue band in this figure. Again, as you can see, our result is consistent with the GM18 X feeder and the initial analysis of Fermi-Lab data. So our result, this means our estimate favors the beta around 1 instead of 2. Then, of course, this calculation can be improved. For example, this calculation, we use the NIL matching formula, which can be improved. And as we emphasize, this calculation is unphysical Pion mass, and the physical Pion mass calculation is necessary. Then, of course, Carroll symmetry is important for Pion. Therefore, we could also have calculations with Carroll formulas. So recently, the NL matching formula is available, so that we can extract the PDFs from lattice data at NL accuracy. The Wilson coefficients actually evolve the lattice data as a function of z to the scale mu in MS bar scheme, so that when the lattice data distributed in a large range, the logarithm could be large. So one may need to include the decay lab evolution by solving the RG equation. By taking this into account, let's see the figure on the right. So at the leading order, which is the Cn equal 1, we can extract the moments, and as you can see, the red point at leading order, the clearly Z naught or Z dependence can be observed for the moments. And then beyond the leading order, the Wilson coefficients evolves the lattice data from Z naught to the factor scale mu with that. So it should be independent of Z naught if the evolution is good. As you can see, the NLO result, which is showing as the origin point, is actually consistent with the NLO result as the blue point. Although they are within current statistics, though they are more flat and stable. They also agree with the Digger lab improved the case so that we will use the fixed order NL matching formula for the following analysis, but probably they will produce similar result to the NLO case. Then we have a calculation with a physical Poincare mass using Wilson Clover fermion. In this case, we have Poincare mass at physical point, and the largest momentum in this case is around 1.8 GeV. So that we can have ZPZ up to around 6. And then we have a calculation of using Carroll fermion, which are the domain wall fermion, unitary domain wall fermion calculation. In this case, we have two sets of data with momentum up to around 1 GeV and the result in ZPZ around 4. As we have discussed, the NL matching formula can describe the evolution of the data very well. So we perform a combined analysis of the lattice data in a range of Z. Z is the lattice data set to the scale of lattice data. So by the combined fit, we can stabilize the fit and try to extract the higher moment. So as you can see from the left figure, using the Wilson Clover fermion at physical point, we are able to get access to the 6th order moment. And on the right figure, we are showing the moment extracted from a domain wall calculation, which limited by the statistics and the momentum. They are not there, but it looks pretty consistent with the Wilson Clover calculation on the left. So to conclude, we just put all our calculation in this figure for the moments. On the right part of this figure, we show the 3 sets of Wilson Clover calculation in which 2 of them are using amphithecal Poincare mass and 1 is at the physical point. So as you can see, the mass dependence of these moments of PDFs is quite small. And so that could suggest that the mass dependence of the Poincare mass PDF is only mu, at least within current statistics. So that we simply perform a continuous extrapolation and compare with our previous result and the global analysis result. You can see a good agreement can be found with our previous determination and GM18 and the X feature. And the Wilson Clover calculation result is also consistent with the domain wall calculation, which means that the using of the Wilson Clover didn't bring trouble to determine the Poincare valence structure. So as what we have did, we can pick a model and put into the formula and fit our lattice data. Which is showing as the red band in this figure. For comparison reason, we showed our previous determination as the blue curve, which is the central value of our previous determination, and we also compare with X feature and GM18 result. As you can see, actually they have they are consistent with the error, which means we even use NLO calculation at physical point, our results still favor the beta around 1. Of course, there's still some improvements that we can do, like we can do further improvement of the perturbation matching kernels. For example, as we plot as the black curve in this figure, which comes from the NLO plus NL threshold resummation matching formula. As you can see, the central value shifted a little bit, but they are still consistent within the error, didn't change much. That is because the threshold resummation generally have large impact for the large higher moments of the PDFs, and our lattice data are mainly sensitive to lower moments for now. So we would expect to have more statistics and large momentum to extract the higher moments. Then, in addition to the Poincare PDFs, we also have a calculation of Poincare form factors. That is because on the one hand, we would like to investigate the three-dimensional GPD in the future using similar methodology, which is a hybrid, actually a hybrid of PDF and form factors. So they are key ingredient for the study of GPDs. Secondly, from the form factors, we can extract the Pion charge radius, which has been precisely determined from the experimental data. So for back comparison, we can cross-check. We can check the accuracy of lattice calculation. Then this is the beginning of calculation with HQ square, which will meet the AIC measurement in the future. So here we directly show our result, result as we're using a Pion mass at physical point and a single but fine lattice spacing. Our result is showing at the blue point. It is on the left figure. You can see the form factor we get actually overlap with experiment data from Sun and the dispersive analysis from Colangela. This is quite encouraging, and so we perform the experiment fit of our lattice data and to try to determine the charge radius of Pion, which is showing as a green point in this figure. And you can see our results actually have good agreement with the BDG value. Okay, yeah, that's it. We studied the Pion valence quark PDF with multiple lattice and the Pion mass, and we found the Pion mass dependence, the mass dependence of the Pion valence structure is smooth, and we found the using of Wilson clover Fermi didn't bring trouble to the determination of Pion valence structure. Finally, we have a calculation of Pion form factors, which have good agreement with the experimental data. Yeah, that's it. Thanks.
Thank you very much, Xiang, for a nice talk. Do we have questions? Remember that if you have a question, you have to raise your hand. And if not, I do have a question on slide 9.
9. Okay.
When you show your Pion, the results from the field. What makes your uncertainty band narrow at around x 0.6? Because it narrows down and it spreads back. So what's so special about that point?
I think that's because the form of the model we pick here, they have the favor to have a narrow band at this region. And maybe we can try to more form to, yeah.
I mean, it looks a bit funny. Like it just narrows in one particular place. It's a bit strange, but okay. Okay. Further questions? Okay, if not, thank you very much again. We will move to our next speaker, Christos Kallidonis. So, Christo, if you can please share your slides. And I will let you know when you have 2 minutes to finish. I think you're muted.
Okay, now you can hear me?
Yes, go ahead.
Sorry about that. So I'm Christos Kallidonis. I'm a postdoc at the Theory and Computational Division at Jefferson Lab. And in this short talk, I'm going to show some recent results on the Nucleon valence quark distribution functions from an exploratory Lattice QCD calculation using the pseudo-PDF framework. So this work is part of the Hadstruct collaboration, whose members I list here. And in this talk, I'll start with a short introduction before saying a few words about the pseudo-PDF approach, which we'll be using. Then I'll show how we evaluate the related matrix elements on the lattice. And of course, I'll show the X dependence of the PDFs. And finally, I'll conclude. All right, so the pattern distribution functions, or PDFs, in the pattern model, they have a probabilistic determination as the number density of partons with a longitudinal momentum function X of the nucleon momentum. These objects are accessible in deep inelastic and semi-inclusive deep inelastic scattering, experiments. And even though this is a difficult procedure, there is still some good precision for the unpolarized PDFs. Now, since the PDFs enter a variety of important applications, including W boson mass calculations related to the strong coupling constant, as well as Higgs boson couplings and cross sections, which may help probe beyond standard model physics, makes them a particularly hot topic, and therefore lattice evaluation is particularly timely. In addition to that, a lattice evaluation provides a first principle calculation of these quantities. And since the unpolarized PDFs are well constrained from experiments, they can serve as a benchmark quantity for the transversity PDFs and the GPDs and the TMDs, which are even more difficult to obtain from the lattice. Now, the unpolarized PDF is defined as a non-local matrix element on the line cone in Minkowski space, and I show the expression here, where this is a nucleon state with momentum p. This is a Wilson line along the light cone, and the light cone coordinates are denoted with xi plus and minus, and the notation for the plus and minus is shown here. Now, these light cone coordinates, the light cone distances shrink to the origin in the Euclidean space-time, and therefore accessing directly this matrix element on the lattice is not possible. However, through the years, there have been a couple of methods for accessing the X dependence of the lattice, and I list the most prominent of them here. Actually, the quasi-distributions introduced by Jiang Ji in 2013, as well as the pseudo-distributions introduced by Anatoly Radyushkin more recently, are, I would say, the two most prominent methods for computing the PDFs on the lattice. And in this talk, I'll be focusing on the pseudo-PDF distribution. Now, very briefly, the steps towards the X dependence within the pseudo-PDF, I list them here. So we have to compute appropriate matrix element. Then we have to take care of the divergences and the renormalization associated with those matrix elements. Then we perform a perturbative evolution, which gives us the light cone distribution. And finally, we perform a Fourier transform, which reconstructs the X dependence on the PDFs. And I'll show these steps as I go on in this talk. All right, so in Euclidean space, we have to consider this matrix element over here, where again, N of P are boosted nucleon states. We have a Wilson line, and then we consider the vector current here since we want to compute the unpolarized PDFs. And this matrix element can be decomposed into two terms. One term contains the leading twist plus some residual higher twist contributions. And the second term is purely higher twist. And with a particular choice of our kinematics, which I show over here, and we also consider alpha equals 0 so that we get the gamma 0 matrix element over here, we can isolate the leading twist contribution. And this contribution can be written in terms of two Lorentz invariants. One is the so-called Joffe time, and the other one is the Z3 distance. And this matrix element again is also known as Joffe time distribution. Now, in the pseudo-PDF approach, one would perform a Fourier transform along the constant Z3 line, which will give access to the so-called pseudo-PDF, which can be considered as a generalization of the actual PDF at non-light cone distances. I mean, at non-zero light cone distances. And then by performing a Z3 going to 0 limit, one would get the PDF. This is, of course, while ignoring the divergences that are associated with this matrix element, which features a standard logarithmic divergence. It also has a power divergence due to the Wilson line entering over here. However, it is multiplicatively renormalizable to all orders in perturbation theory. All right, so on the lattice, what we do in order to obtain these matrix elements, we compute correlation functions. So one type of correlation function is a 2-point function, which I show over here schematically. So at some point on the lattice, we create a particle state with the quantum numbers of the particle we're interested, in this case, the nucleon. And at some later point, so this is called the source, and at some later point, which we call the sink, we annihilate this particle state. Another correlation function we consider is the so-called 3-point function, where we create the particle state, we couple the current on some intermediate point, and then we annihilate the state again. Now, when we deal with correlation functions of the lattice, we usually perform some kind of smearing, as we call it, because this helps increase the overlap of the interpolating field, which creates and destroys the state with the ground state of the nucleon. And the standard technique is to consider some gauge covariant form, which is based on a 3-dimensional Laplacian. Now, another method was introduced by Mike Peardon some 10 years ago. And in this proposal, the smearing operator is approached by a low-rank eigenvector representation of the 3D Laplacian. So we compute the n first eigenvectors of the Laplacian, and then we apply this operator on the quark fields that enter the interpolating operators. And when we do so, we can express that correlation functions in terms of objects we call perambulators, elementals, and generalized perambulators. And the inversions are they take place over the eigenvectors of the Laplacian over here. Now, the advantages of this method is that it allows for a factorization of our correlation functions. We can obtain various spin structures without additional inversions of the Dirac operator. There is momentum projection done both at the source and the sink, which allows for a better capture of the lattice. And also we can reuse these building blocks for different particles or different observables without the need again for additional inversions. And the disadvantages is that we need to take an extra step for every gauge configuration, and that is to compute the eigenvectors of the Laplacian. And this can actually result in big files, and sometimes we have storage issues. Now, the simulation details. We consider a single gauge ensemble with the Wilson-Clover fermion action with 2 light quarks and plus a strange quark. Our lattice volume is 32 cubed times 64. We have a lattice spacing of about 0.09 Fermi. And the pion mass for this ensemble is around 350 MeV, which is away from the physical point, but that's okay for a first exploratory study. And here are the parameters of our calculation. We have around 350 gauge configurations. We have 4 time sources, which allow us to increase our statistics. We have 6 non-zero values of the boost momentum, which correspond to about 2.5 GeV at the highest boost. We have 12 values of the Z3 displacement for the gauge link with a highest value of about 1 Fermi. And this basically sums up our statistics to about 5,600. We also use 64 distillation vectors, and we have 6 source sink separations in order to examine the excited state effect. Now, all these runs have been performed at the JLab computer clusters and also at Frontera using the Chroma software suite and some in-house analysis packages. All right, so having computed our correlation functions, we form a ratio of the 3 and the 2-point function, which in the large time limits, it is expected to give us the desired matrix element. And since we want the valence quark distribution, we consider the real part of this ratio. And to get the ground state matrix element, we consider 2 methods. One is the so-called plateau method. The other one is the summation method. And please feel free to ask more questions if you want. And I'll be happy to explain how we do these methods. But very briefly, I'm just going to see here that we perform some kind of fits on this ratio, and with some criterion, we choose the final value of the matrix element for each momentum and displacement combination. All right, so after we obtain this matrix element, there has been some suggestions in a series of recent papers by the Hadron collaboration that we need to divide those matrix elements with appropriate factors, which satisfy some conditions. And it turns out that a good choice to divide the matrix element is the corresponding matrix element at 0 momentum. And furthermore, so by dividing over here, we get this matrix element, right? And then by considering the renormalization of the vector current, and we choose a momentum dependent normalization to take into account lattice artifacts, we end up with this double ratio, which we call reduced Joffre time distribution. And with this ratio, the multiplicative factor coming from the gauge link normalization cancels out. And it's also expected to have some partial suppress of the higher twist contaminations that enter this matrix element. And I show here how this reduced Joffre time distribution looks like as a function of the Joffre time. And we see that while in general the points fall on a universal curve, we have some discrepancies, especially at higher values of z. Of course, here the error bars are too large to say anything meaningful, but we expect that those points will eventually come to the universal curve with the perturbative evolution. Now, before I'm sorry?
2 minutes.
Okay, so I have to rush a little bit. So before I move on, perhaps I should say that we have some preliminary results from 2 other ensembles that will help us examine pion mass effects and volume effects. Now I should say a few things about the perturbative evolution. So this is the expression up to 1 loop. So here we have 2 terms. The first term is to evolve our data to a common scale, and we also convert them to the MS bar scheme, which is standard in phenomenology, for example, if we want to compare. Now here we treat each 3 value independently, and we also perform a polynomial parametrization of our Joffre time distribution. And here we something we want to check this is an ongoing progress. We want to check the effect of performing evolution and the conversion together or separate procedures. So here with the colored points, I show the results of this evolution, and the gray points are the original data I showed before. And we show that while there is some difference on the original points, we still have some residual discrepancies, and we are currently studying those discrepancies. We want to see if it's just a failure of the evolution or if there's some residual higher twist effects. All right, so the next step is to construct the X dependence of the PDF, and we need to perform a Fourier transform. However, this is an inverse problem, as we say, because we have discrete data in the new space on the left-hand side, and on the right-hand side, we have a continuous function in X space. And one way around this, perhaps the first iteration around this, is to choose a meaningfully functional form of the X dependence, and which actually introduces a model bias in this determination. But this is a first step again, and what we do, we perform this fit according to this chi-square over here, where this QFT are our discrete data, and then Q nu mu over here is just this integral where the fit parameters alpha, beta, and delta are left over here. And by doing so, we get this curve over here. So we perform this fit up to Z3 of 8 and 12. And we see actually that there is not much of a difference in the resulting curve. Now, with this fit, the final X dependence of our PDF looks like this, where in blue is our data and the other three curves are phenomenological results. And while we see there is some discrepancy, this is expected because we're not at the physical point. We haven't considered any systematics, but still we think that this is a pretty good preliminary result. So I'll just conclude. Now, the Lattice QCD via the pseudo-PDF network framework appears to be in good position to give reliable insight on the Nucleon PDFs. The distillation method provides a valuable alternative to standard mirroring techniques, and we have controllable statistical uncertainties and excited state effects. Now, as I mentioned before, the stretch between the lattice and the phenomenological X dependence can be due to lattice artifacts, and also due to the parameterization of PDFs. And we are currently in the process of examining both of those systematics. And of course, we want to compare with other lattice calculations. Now on the horizon, we need to finalize the results from the other ensemble in order to study volume and pion mass effects. We want to study ensembles with a smaller lattice spacing so that we can do a continuous extrapolation. And of course, we have the helicity, transversity, and the GPDs on the way. And of course, we are also considering disconnected diagrams. And that's all I had to say.
Thank you very much, Christos. We have one question here. Yeah.
Hi, nice talk. So I have a question about your Fourier transform on your last second slide. Yes. So yes. So to reach the nu as large as like 14, I guess it's because you have used large data with large Z3. That's a 12 times A.
Yes.
Yeah.
So we go up to momentum 6, yeah. And at the largest Z3, of course, this we have a factor of the unit momentum in front, based on spacing, and that gives us this large nu value. Yes.
Right. But as you mentioned that you are not sure if the higher twist corrections are sufficiently suppressed with this large Z3.
Yes.
So for example, your blue points are not lying on the same universal curve. Mm-hmm. So I wonder how you can even do the evolution in this scale and how you can control these higher twist corrections.
Yes. That's a really good question. So again, this is an exploratory study. So we're at the process right now of I moved one slide back just to be here on the evolution. So we are in the process now of examining how big the effect of the evolution is for each Z3. And also how in order to see just the effect of the evolution, we need to take out the Ebers-Bar scheme conversion, because this is nu dependent. So we have to take this out just to see how the evolution affects our data at different Z3s and at different nus at the same time. And in addition to that, we are considering. And one thing we can do is to plot the offset time distribution for small values of Z3. Say, put a cutoff at Z3, say 6 or something, and then plot our offset time distribution and see if it falls on a universal curve, for example, right? And then plot the offset time distribution for Z values greater than 6, for example. And this way we can see, in fact, if the large Z3 points are all outside the universal curve, Or the other thing we can do is actually take points which are the same nu but different Z3, for example, those here, right, where you see that are the same nu but they differ. And if I plot those, I can see if actually they have a logarithmic dependence and where this logarithmic dependence stops. So if the logarithmic dependence stops at some Z3 value, say 6 or something like this, then we can say that, okay, we can leave the large Z3 points out, right? And then redo the fits. But the reason I'm showing both fits over here is just to sort of demonstrate that the fit is basically constrained by the small nu values over here. And even if I include the large Z3s, which don't even fall on the universal curve, the fit doesn't change significantly.
Okay, so let me understand what you mean by universal curve. So you see that the data points overlap with each other very well for nu, say, smaller than 3. Then by universal curve, you mean beyond nu equals 3, do you mean you extrapolate beyond that point? Is that what you suggest?
Yeah, so I mean, if there were no residual higher twist effects and the evolution would work great, you know, for all, for even very low scales, which correspond to Z3 values, I would expect those 3 points, those 4 points, for example, to fall on this curve as well. And also these blue points over here. I mean, here the errors are perhaps too large to say anything, but let's go here where the momentum is small. So I would expect those points to, again, you know, be a little bit higher so that they are on the universal curve. And this is a first indication actually that either the evolution fails or there are higher twist effects. And that's why we need to make those systematic checks to actually determine whether it's just a higher twist effect or if the evolution basically leave those points completely unchanged.
I see. So your blue curve.
All right, I'm gonna use my powers as chair because we're running out of time and we're already taking over the coffee break, which will be super short. So I will request further questions to Christos to be done on the chat, and we will move to the next and last talk of this session. So Yushan, if you can please share your slides.
Okay, let me share my screen.
And I will let you know when you have 2 minutes left.
Okay, thanks. Can you see my screen?
Yep.
Yeah, okay, thanks. Hello, everyone. I'm Yushan Su. I will be a graduate student at the University of Maryland. Today, I'm going to talk about the self-renormalization of quasi-Light-Front correlators on the lattice. This work was tutored by Professor Xiang Gao. First, let me briefly introduce the background. Large momentum effective theory proposes an effective way to get the pattern distribution function from lattice data. It suggests that one can start from calculating the quasi-Light-Front correlator on lattice. It is a matrix element with a quasi-PDF operator in the middle, and it has the external state in a very large momentum. And you can do renormalization of this matrix element, and then you do Fourier transformation and matching, and finally you can get the PDF. Here, renormalization is very important. And because we have a Wilson link in the quasi-PDF operator, and the Wilson link has the self-energy, and the self-energy will gives you the linear divergence. Actually, you can calculate this factor explicitly using the Feynman integral, but here we can also understand this in a more intuitive way. Since the Wilson link can be mimicked by the heavy quark field, and this is very much like the non-relativistic limit, just like the Coulomb potential. If you integrate over the Coulomb potential, you can get the linear divergence. And on lattice, in the matrix element, this linear divergence factor will become an exponential factor here. And you can get this through the functional method. You can also get this through combining several pieces of Wilson links. And anyway, you have an exponential factor here. It has the 1/a dependence and the linear z dependence. It will be dominant in the matrix element, and it is unphysical. we must get rid of this linear divergence factor. That's why renormalization is extremely important. Here is the outline of my talk. First, I will give a test of linear divergence. Then I will present the self-renormalization procedure. And then we will apply the self-renormalization method to the Arum factor and the zero momentum hadron matrix elements. This can be calculated on lattice. I mentioned before that the linear divergence will have the 1/A dependence and the linear Z dependence in the exponential. So we must test it in the lattice data. And for example, for the Arum factor, and if we take a natural log on the Arum factor, we will expect it in this form. And then we will use this form to fit the lattice data. For each Z, we just fit the dependence on A, and we will treat EZ and GZ as fitted parameters. And you can see that for each Z, you can really see the 1/A dependence. And we can also use this function to have a reasonable fit. And then we can get EZ after the fit, and we can plot EZ as a function of Z. It shows that the EZ has a linear dependence on Z. So both 1/A dependence and linear Z dependence have been tested. Before I present the self-renormalization procedure, first we need to modify the fitting function. And we can, since the linear divergence is very sensitive, we need to take care of every details. We need to include the discretization error. We also need to include the resummation of log divergence. Here are 3 steps of the self-renormalization method. For each Z, we use this fit function to fit the A dependence to extract GZ. Here we will treat the lambda QCD as a global fit parameter, and the G, F1, F2 are fitted parameters. We can get the GZ after the fit. However, the GZ will contain the non-perturbative renormaling effect. So we must need to get rid of this renormaling effect. We do this through matching the GZ to a continuous scheme, such as the MS bar scheme. We use this equation to fit the M0. And it can only be done in a small Z window. That is the region where the perturbation theory can work. And then we do the M0Z subtraction to get our final result, the residual intrinsic physics. For example, if you would like to self-renormalize a zero momentum nucleon state quasi-Light-Front correlator, and you take step 1, for each Z, you fit the A dependence. And here we determine the lambda QCD through the global fit. After we determine the lambda QCD, we can use this function to fit the data. And for each Z, we fit the A dependence. And you can see that the chi-square over degree freedom is about 1. It shows a good fit. We can get GZ after the fit. And then we fit the M0 in a small Z window. Here we chose a window like this, where this is the region that the perturbation theory can work. And then we subtract the M0Z to get the residual intrinsic physics. It is the blue curve. The black curve is calculated perturbatively, and the black curve and blue curve are consistent at small Z. That means you can really match the lattice results to the continuous scheme at a short distance. To test the self-renormalization method, we can define a renormalization factor. Here it is. All the parameters here are either fixed or fitted during the renormalization steps I just mentioned above. And you can divide the Bayer matrix element by the renormalization factor. Here I show the results for different lattice spacing. And the result shows little dependence on A. That means our renormalization method works very well. Then we apply the self-renormalization method to different matrix elements. We can apply it to the hadron factor, and we can also apply it to the hadron state matrix element in zero momentum. And they can be calculated using the overlap valence Fermi action. And they can also be calculated using the Clover valence fermion action. And in the self-renormalization steps, we can get the linear divergence parameters. And for the unsmearing case, we can fix the K as the one loop perturbative value. And we can get the lambda QCD through global fit. And you can see that the lambda QCD for the hadron matrix elements are similar to each other. However, the lambda QCD for the hadron factors are different from those of hadron matrix elements. That means the linear divergence for the hadron matrix elements are similar to each other, but the linear divergence for the hadron factor are different from those of hadron matrix elements. The same situation happens for the heap smearing case. That means if you use hadron, you cannot eliminate all the linear divergence. Then we pay attention to the residual intrinsic physics. For example, for hadron factor, the blue curve is the residual intrinsic physics obtained from the self-renormalization based on lattice data. And the black curve is calculated perturbatively. And they are consistent at small z, but at large z, there is large discrepancy. The same thing happens for the zero momentum pion matrix elements. So that means there is a large extra non-perturbative effect at a large distance in hadron and ratio scheme. And this extra non-perturbative effect cannot be compensated using the perturbative conversion or matching. So that supports the hybrid renormalization method proposed recently. Then we can make comparisons between the Clover and overlap valence fermion actions. And the blue curve is calculated using the overlap valence fermion actions, and the red curve is calculated using the Clover valence fermion actions. And the results are similar to each other. And then we can make comparisons between the unsmearing and the heap smearing cases. The blue curve, the red curve is the unsmearing case, and the blue curve is the heap smearing case. And the results for heap smearing and unsmearing are similar to each other. That means heap smearing will not change the residual intrinsic physics. Actually, that's easy to understand because the residual intrinsic physics is a long-range behavior, and heap smearing only changes the short distance behavior. So we can make a conclusion. We propose the self-renormalization method. It works well in disentangling the renormalization factor from residual intrinsic physics. And linear divergences for hadron factors are different from those of hadron matrix elements. And third, we observe a large non-perturbative effect at large distance in hadron and ratio scheme. That supports the hybrid renormalization method. Finally, Clover and overlap valence fermion actions, unsmearing and heap smearing lead to similar residual intrinsic physics. So you can use all of them to perform lattice calculation, and that will not change the physics. That's all I would like to talk. Thanks.
Right, thank you very much. Do we have questions? Yes, please.
Yes, I just want to make a comment about Yong's question about the previous talk. And this is relevant to this talk because what we have done is to show that after the look at the renormalization factor for Z greater than roughly 0.25 or 0.3 Fermi, there's a large non-perturbative effects. And so therefore that if one does a coordinate space expansion and we cannot use the data for Z much greater than, let's say, 0.4. And so therefore, if Z cannot be used for greater than 0.4 because of high twist effect, so that means your UV time cannot be, or Lycon distance cannot be much bigger than, let's say, 6 or 7. Okay. So anyway, that using the data with large correlation lens in the coordinate space expansion, we have intrinsic large non-particle effect. Well, high twist effect.
All right. Do we have further comments or questions?
Does it answer your question, Yong?
Yeah, but since they, I just want to know if they vary their model choices, they can indeed see that universal curve, because if you are contaminated by higher twist effects, it's really hard to tell whether your extrapolation to that large value of nu is still reliable. Yeah, that was my previous question.
You cannot have a universal curve. The universal curve only means you have a twist-2 dominance, right? The universal curve is you taking the large momentum limit, you have a twist-2 dominance, and then you have a universal curve. If you have a car twist effect, you cannot have a universal curve unless you take the PZ go to infinity limit. And so for finite PZ, you cannot see it because of a higher twist effect, as shown in this plot. So anything beyond Z go to 0.3 or 0.4, you're going to have a large non-perturbable effects or higher twist effect here.
Yeah. Yes.
So that limits very much that how much you can do with the you know, the quasi-Lycon distance.
Yeah, I can see that. Thanks.
Yeah.
All right, we have one more question and then we can go to the coffee break. Please go ahead.
Hi, can you hear me?
Yes.
Hi, that's a nice talk. I have a question about the speak of Yushan Su. So I would like to know what is the RIMOM factors and what's the difference between RIMOM and the hadron matrix element? I'm not sure because there's no explanation about RIMOM, I think.
Yes, RMO factor is the quasi, you have a quasi PDF operator and it's in the quark state.
Okay.
You calculate this matrix element in quark state, you can calculate it on lattice.
Okay, thank you. I see.
And the zero momentum hadron matrix element is this, and it's a quasi PDF operator in the hadron state.
I see.
You can calculate both of them lattice.
Thank you.
Right. Thank you very much to all the speakers in this session. I declare we can go to the coffee break and then see you all at 4 p.m. European time or 10 p.m. East Coast time. So enjoy your coffee break and see you in 12 minutes.